Hi there. Have you ever been participating or hosting an educational activity and being confronted with the problem of composing groups of participants and assigning topics to them, such that on the one hand, their satisfaction with the topic and with their teammates are maximized, but also such that their individual capabilities synergize and reach some diversity. Because if you find that question interesting, then you might listen to this presentation, because that's exactly the question that Thomas and myself investigated as part of our master seminar at the Working Group for Management Science and Operations Research at the Chair for Economics and Law at TU Darmstadt this semester. And we are glad to be able to share our results with you. So why are we recording this video? We had 3 groups of people in mind when we decided to record this. The first group is most likely you, so the generally interested viewer, which might get some inspiration or build upon our ideas, just genuinely interested. The second group we thought about was potentially future users at the chair, because the chair intends to use this software to actually execute the group assignment in the future, if it's sufficiently good, what we created. And the third group of people are Thomas and myself, because it's always good to practice the presentation skills and just have a practice run, what we will present in 1 week time. So let's get started. This will be our today's program. So we will start by stating our problem, identifying stakeholders and their interests, and giving an overview over the path we are going to take towards our solution. After that, we will start with some basic model which was provided to us by the professor which hosts our very seminar this presentation is part of, namely Professor Weidinger and his assistant, Mr. Wild. And this model was to be optimized, improved by us, namely reducing the constraints and reducing the number of decision variables. This we did, and then we will show you some performance comparison before we'll extend the model to also be able to assign topics to the groups that have been generated. After that, we will further extend the model such that also certain aspects of skill distribution are considered, namely a fair distribution of experiences or a certain level of diversity within the groups. And then we will use this extended model to approximate a kind of efficient frontier of a multi-criteria optimization problem by combining a blended and an hierarchical approach to find Pareto optimal points of this problem. And in the end, we will look at some numerical results to conclude this presentation. So let's get started with the problem description. This was the original task. I've highlighted the most important words. So it's all about preference satisfaction regarding topics, regarding other people, a balanced group size, evenly distributed knowledge, and it's a multi-criteria optimization problem. Apart from this text, we were free to design whatever we thought was useful. So we decomposed this text into this table of stakeholders and their interests. So we have students which want their topics that they are interested in, but they also want to be in a group with their mates. And we have the stakeholders, two other stakeholders, namely maybe the professor and possibly his assistant, who want a fair and balanced distribution of skill and size, and maybe a certain diversity within the groups regarding their respective skills. And we have the chair, which want a cost-efficient, versatile, easy to use, quick application to solve this problem. So all the models we will present today will meet the criteria of being applicable to any seminar, so versatile, intuitive to use, and open source or free to use university software only, so that nobody has to pay for it. And the runtime should be well under 1 day on moderate hardware, such that the students get their assignment quickly. So all that needs to be satisfied now is the actual multi-criteria optimization problem. But why is it user-friendly? Isn't this very abstract and mathematical? Yeah, it is, but we have this layer approach. So the user itself mainly interacts with Excel, where he or she inputs the data he or she evaluated from the students regarding their preferences, for example. And this gets read into a Java program, which itself is backed up by the Gurobi library, which actually solves these binary or mixed integer programs. So the user itself only has to interact with Excel and then put in their preferred destination for the resulting file, and then hit run in their Java IDE of choice. All right, so let's concentrate ourselves on this multi-criteria optimization. For that, we will construct basically 4 models, which will get increasingly more advanced. So as I said, we start with the basic model in its different forms, then we extend it for topics, for the skill distribution, and in the end, we compute some efficient frontiers. And as you can see, the amount of goals the models will satisfy increase with the model complexity we employ. So we will start with only social satisfaction, then topic satisfaction comes into play, and then also the skill distribution and diversity. The notation we're going to use is the natural numbers start at 1 for us. If we want the 0, then we will write index 0. N in brackets is natural numbers from 1 to n. There will be S number of students, G number of groups, and T number of topics. And the respective groups of students, groups, and topics will be identified by an enumeration of natural numbers. So let's look at the basic model that was given to us. Here we have parameters QSS prime, which model whether or not person S wants to be in a group with person S prime. And person S may only hand out one of these once. To all the other people in this seminar, there will be assigned a 0. You might also assign nobody to U1, but that's your choice, but at most one. And then you also have the minimum and the maximum group size determined by the professor. As decision variables, you have binary variables, whether or not person S and S prime are together in a group. Yes, 1, no, 0. The problem is a binary program where we have as objective a function that counts the number of wishes of the students which were fulfilled. And then we normalize it by 1 over S such that the objective is between 0 and 1 to make it easier to interpret and independent of group size. Then we have the group size restriction, which is with -1 on both sides because we are not counting this person which we are looking at that inequality. So we have as many inequalities as people. So they obviously are redundant, but yeah, at least in combination with the other constraints. But this person S is not considered. So without this person S, there have to be at most M over bar -1 at other people in that group, other people. And that's why there's a -1 on both sides. The second constraint is some transitivity condition, which makes sure that the intuitive understanding of what the relation being in a group together should mean is fulfilled, namely that when a person is together with another person in a group and this person is with the third person in a group, then also the first must be with the third person in the same group. Transitivity of this relation. And the third constraint is just the symmetry. Yeah, and then binary values which can be attained. All right, so but we immediately see there are some redundancies. We have the symmetry and we actually don't need this. So this was our leverage point to improve this model. And now we have seemingly the same variable, but the devil is in the detail, namely in the quantifier. So we only consider S smaller S prime. That means that this decision variable can be represented as a matrix where you only have the elements lower or upper the diagonal, however you want to see it, but only 1/2 of it. And instead of the whole matrix, except of the diagonal, of course. But we reduce number of variables by the factor of 1/2 by this. And for the constraints, we actually have exactly the same constraint as before, but they look a bit different now, despite meaning the exact same. So constraint 4 is the same as before, just that now we don't sum over one row of this XS prime matrix, but when this row hits the diagonal, we go up 90 degrees. And by symmetry, that's equivalent. So this is, again, the same thought process behind this group size restriction from before. And now we have 3 conditions which all model transitivity. Why is that? That is because now we only have these X variables for increasing indices. And therefore, we cannot just write pairwise distinct as on the slide before, but we have to consider all the permutations which were allowed before, but only those which are increasing now. And there are 6 permutations, and only 3 of them are increasing. Therefore, we only have 3 over 6, namely 1/2 as many of these transitivity constraints as before. And as you can see, we also completely spared out the symmetry constraints because symmetry is embedded in our model because we have no redundancy by symmetry in our model. Yeah, so this constraint is also missing compared to before. So as I said, as well, variables as well as constraints are reduced around by a factor of 1/2, and that in fact shows also up in our runtime comparison. So these two models were applied to the same 100 randomly generated instances of grouping problems. How they are distributed is in the appendix video if you want to have a look at this later. But as we can see, the mean running time is almost reduced also by a factor 1/2, a little bit worse, but it's pretty significant, and the improved running time almost always fully dominates the naive one, except for some outliers. But in general, this simple modification really proved its value here. So now we will extend the model to also be able to assign assign topics to shared groups. Here I have an example of this very seminar itself. We have 6 participants. Thomas is my teammate, so we are in one group. The other 4 participants are in group 1. And then there is this next to the student, the group layer, the topic layer. We all deal with the same topic. That's why big T is equal to 1, capital T. Now we have variables that model which person is in which group. They are binary, whether or not person S is in group G. And we have preferences of person S to be in a group with another person S prime. And now they are continuous, so they so that you have a more granular adjustment how much you like to be in a group with somebody. And then there are the variables YGT, which model whether or not group G deals with topic T, and PST, which is the preference of person S to work on topic T, and that's also a continuous variable. And now these variables together form our objective. So we have one objective one summand of the objective we will later see that quantifies the social preferences. So as it will turn out, A S prime G will be 1 if and only if S and S prime are together in group G, and if you sum over all groups. And keep in mind that everyone is in at most and exactly one group, then this sum is 1 if and only if they share a group. And if they share a group, then we add this term, which is just the social preferences of these 2 persons together to each other. And then some lambda, which you will see on the next slide. And this will be normalized by 1 over S. Why this is normalization, in fact, you will see also on the next slide. And the second summand of the objective models the topic satisfaction. So BSGT is 1 if and only if person S is in group, person S works on topic T via being in group G. And again, everyone is in exactly one group. Summing over G means, okay, this sum is 1 if and only if person S works on topic T anywhere. And then if this is 1, we get rewarded by PST or punished if this person doesn't like this topic in the objective. And here's also this weighting factor, which we'll explain now. Namely, everyone gets in total 1 vote. And he or she can decide how much of it can be assigned to his social preferences and how much of it will be assigned to its topic preferences. So if this person doesn't know anybody there, probably will choose lambda to be a small value and maybe 0. then all of its vote will go into getting the topic he or she desires. Other way around, if the topics are all good, for example, and you want to be with your buddies, then you might choose lambda gleich 1. So, but why is this normalization 1 over S? Well, we take those preferences Q as bar, and we write a tilde over it because we will normalize it using the L1 norm. As long as not all entries are 0, then it remains 0. But other than that, it will be normalized such that the absolute value summed up over all the preferences will be 1, so that you can't exaggerate your vote and kind of do some strategic voting by choosing your friend to be 1 and everyone else -1 or something. This will just be normalized to 1 over S and -1 over S for everybody else. So you're diluting your influence. It's always a trade-off, voting for many people or voting for few people but stronger. And we do the same with the topic preferences, also normalizing it with the L1 norm. So these are the parameters we need for our advanced model. So as I said, Q and P for the social and topic preferences, lambda for the weighting between the two, and then M underscore and overline M for the minimum and maximum size of a group that works on a certain topic. So now you can adjust the minimum and maximum size depending on the topic the specific group works on. And we introduce also a topic-specific minimum and maximum number of occurrences of a certain topic within the seminar. So what is the problem in its fullest? Parameters we have discussed. Now variables, A as S prime G, I've already said, is 1 if and only if S and S prime share group G. Here SGT is 1 if and only if S and group G have a topic T, and the other one I already explained. And now we have the binary program to all of this. The variables are not so interesting. We have already looked at them. So let's focus on the constraints because the objective we already investigated. So now to the constraints. We have 8 constraints. And the first one is just everyone is in exactly one group. The second one might seem rather unintuitive, maybe unintuitive at first sight, because it states that every group has at most one topic. And now you might ask, why at most one? Well, this number of groups, you cannot tell before how many groups there will be because the group sizes only have to be in certain boundaries. So there might be more groups of fewer people or other way around. So there might be empty groups in our model in the end. And these groups should not have a topic because this will have an influence on the objective, but not really on the seminar itself. That's why each group has at most one topic. Then the next one states that empty groups don't have a topic. So if you sum over all x as g with respect to s and they are all 0, then ygt must also be 0 for all t. So this group has no topic if nobody is in it. Other way around, if somebody is in it, then this group must have a topic. That's the next constraint. The next two look kind of funny, but they are actually just a logical conjunction. So AS as prime G is 1 if and only if X as G and X as prime G are 1. So that means, well, this variable which moderates if they are in the same group together is 1 if and only if they are both in group G. So that's just doing what it should. And similarly with BSGT is 1 if and only if really this person is in group G and this group has actually their topic. So that looks kind of intimidating, but it's actually not. The next constraint, constraint 16, models the bounds for the group size. Now, why are there these factors on both sides? These factors are necessary, these y factors, because our bounds are topic specific. So they only hold for that specific topic. The last constraint will bound the topic occurrences. So how many groups have this topic? Well, we sum over the groups and then we have this bounds on, and that's it for all topics T. So now that we have seen the extended model for topic assignment, we go a step further and also introduce some skill distribution aspects into the model. So let's derive it. We introduce some new additional parameters. So h as I is a binary variable, which tells us whether student S has a certain binary characteristic that can be like he is part of the department of engineering or mathematics or psychology. It's really a binary thing, and this will be a hard constraint such that the professor might say in every group is at most or at minimum somebody from this department. And this will be expressed by h lower bar I, which is the lower bound for the hard skill I per group, and similarly with the overline for upper bound. Then we also have some experience skills, ESJ, which quantify how much experience we have with a certain task or skill like programming, statistics, or something in that direction. So something that you can really make an granular estimate for, which is not a binary thing. And then you will have also sigma and mu. Their meaning will get clear in a minute, namely when we look at our two objectives of our extended model. So imagine you have three groups and three skills. And if you sum up the skill points of each of the persons within those groups, you might have something like this. And then our idea is, okay, we want an even distribution of skill among the groups and a diverse skill allocation within the groups. And we do this by punishing via this term. And C upper bar J minus C lower bar J is the difference between the most competent team with respect to skill J to the least competent group with respect to that skill. So this absolute difference in skill will be punished via some negative sigma J. And then we have another term which promotes diversity within the groups. So remember, A S S prime G is one if and only if S summed over all J is one if and only if S and S prime are together in one group. So if they are together in one group, you get a reward of their skill difference with respect to that skill which we are currently summing up over. So it's beneficial for the algorithm to team up different skill levels to foster as much of these points which are waiting here. Yeah, so that's the second objective. The first one should be familiar to you from before. And now we have two objectives at hand. But how do we construct the constraints that we just verbally introduced? Well, as I said, we introduce some new variables, namely C lower bar J and C upper bar J. This should be a upper bar, sorry for that. And ZG, which models whether or not group G is actually used. So to get this Z, we demand it to be greater than all XSG and this forced it as soon as one XSG for any S is 1, it forced it to be also 1 such that this constraint is fulfilled. And if it is fulfilled, we know that this term will vanish. But if not, then this term will be of size S, and size S will automatically deactivate that constraint, because then the right-hand side is certainly larger than the left-hand side. But if we are looking at the regular case where Zj is 1, then we have just this hard skill lower bound, which we demanded on the previous slide, namely that this certain number of people have this skill. And in reverse, here, and you might be wondering, why is here not this deactivating term? Well, the problem was just empty groups might violate this, but other way around is not problematic. And we do exactly the same for the experience. So that's really an analogy. But now we don't have these parameters as hard constraints, but the decision variables, which their difference will be punished later. So those are the constraints. And now we have a multi-criteria optimization problem with those two objectives on the last slide. So that's purely mathematically speaking, maybe a bit a hit in the gut. But yeah, we want to maximize both of these objectives at the same time. So let's generalize this. This is generally a multi-criteria optimization problem, meaning we have a set K of objectives we all want to maximize simultaneously. And Groby Optimizer gives us two possible ways at hand to do so. The first one is a blended approach, namely you have some weights and you just weigh up all the objectives and then you optimize the sum of them. The other one is a bit more involved maybe, but I think you will be you will understand this. It's a multi-criteria hierarchical approach, and you just need an ordering within this set of objectives. And then you have this ordering, and you start with the first objective and optimize it. Then you might get some optimal value. And then you look at your ordering and go to the next one and now add another constraint. And this constraint demands that the new solution to this second objective is not allowed to deteriorate the first objective by more than this tolerance tau. And tau needs to be specified for each of these objectives. So you solve a sequence of k many cardinality of set k many problems. That's the hierarchical approach. Now, how does this help us to approximate the efficient frontier? And what is the efficient frontier in the first place? So for that, we insert a quick definition. Here we have our problem again. A feasible solution X to multi-criteria optimization problem MC is called Pareto dominated if there exists another feasible solution X star, which is not worse in any of the criteria and strictly better in one of the criteria. If that's not the case, this solution is called Pareto efficient or Pareto optimal. So if it's not dominated. Okay, so far so good, but how do we find such points? Well, for that, we thought about this algorithm. What does it do? We start with all the feasible solutions which satisfy the constraints we just introduced. Our set K is pref and skill. We have two objectives. And the number of solutions we saved so far is empty in the beginning. Now we have two two parts of this algorithm. The first one employs this hierarchical approach, and the second one, this blended approach. And in the end, we visualize it, and you will actually see in the end some of our results. So what we do is we do this multi-quadrilia hierarchical approach in this ordering we give it. And we do this for many different orderings and for many different tolerances to really get different points on the frontier. So we do this in the ordering, but now we don't stop. And why we don't stop is maybe a good exercise to pause right here. Why does this not give us Pareto optimal solutions? If you want, you can stop the video because now I'm going to explain. Imagine you have two objectives, like in our case, and the second objective, it's the turn of the second objectives because the first one is done. So now the second one goes to work and optimizes and only has to fulfill, say, 80% of the optimal value from before, and it does so and finds a good solution, the optimal solution with respect to the second objective under this condition. But this does not mean that it's also the best one for the first objective, even among those which maximize the second objective. So it might just, because it doesn't care about the first objectives, it might just lose something on the way, which is relevant to you, but not relevant to the second problem in the sequence, and just waste some potential, even though there's another solution with the same value in the second objective and a better one, the first one. So what we then do for that is we switch the ordering and do the same backwards. So the second one would have this value and say, okay, given my value, objective one, what can you offer me? Have I wasted something? And then there will really come out the best of it you can get. And for that, we do the second for loop. And actually, you don't, this kind of a pyramid approach. And you don't need to optimize 2 times the same objective on top. So here you could actually erase the maximum with respect to this ordering in this set K. So here you could choose a set of cardinality one lower. So then if a solution went through all this process, then you add it to the set. And down there, you solve this blended approach for many different weights, which are all positive for all objectives. And then you want to visualize it. But okay, and now I have this intuition why this produces efficient Pareto efficient solutions. But why is this actually the case? So our theorem states that it is the case, but why is it the case? Well, we have to consider 2 cases. The solution entered here or entered here, the set. So let's look at the blended approach first. Assume, for contradiction, that a solution is dominated. That means at least it is at least as good in every objective, and one objective is even strictly better. And since that weight is also strictly positive, that whole solution would be better for the blended problem. Therefore, the originally dominated problem would never win this blended model, and therefore would not be in the set. So that's the contradiction. The other one works very similarly. So we again assume it was Pareto dominated. Then, however, there exists a largest coefficient with respect to this ordering where it is strictly dominated. And on this backwards part of the pyramid, there it would get beaten by this solution. And then it would get kicked out and replaced by the other one. And therefore, it would not land in this X star set. And therefore, it's again a contradiction. So what do we conclude from this? Well, the set was empty in the beginning. The empty set only contains Pareto optimal solutions, and we only add Pareto optimal solutions. So by some inductive argument, we're done. So, but how does this translate into practice? Well, how do we measure our success? we had our objective, okay, but we kind of scrambled together these two objectives. Maybe it's better to separate them. And then we see nicely what our normalization has done for us. For the skill part, we also had this objective, and here we even do we alter even more, because here these values don't have a real life interpretation, and they're not even normalized. And if you look at the quotient between the lowest ranked team and the highest competent team with respect to some skill, then you get a number between 0 and 1, and it's a really a percentage which you can grab in your mind and do something with it. Which is not the case with this weighted difference, where you don't know what is the real the absolute value of it, because you have different group sizes, etc. So this is really the way to go to evaluate it, we think. For the skill diversity value, we go even further, and we take this, kick out the μj, and also normalize it by computing the ratio to a hypothetical optimal solution where there's always a skill gap of 1 between the skills, which is impossible. As soon as you have 3 people in a group, you cannot have difference 1 between each of them. That's impossible. But just for the sake of normalization, we did this. So in our problems, you cannot actually reach 1, but we surely know in which interval it is. And it's just, yeah, it's easier to grab with your mind. So those are our metrics to our objectives. So what does the numerical tests spit out? So that's a lot to take in, but we can break it down to some interesting observations. So not surprisingly, but in its absolute magnitude, maybe surprising, is the growth of the runtime in S. So we see here that's a factor of 100 in runtime, while increasing the number of students by a factor of 5 in the naive model. In the improved model, we have a similar factor, but in absolute terms, about half as much time. They do produce the same solution, which is not surprising, because they have actually the same problem, just written down differently. But you do have some deviations, namely in these 2 values and these 2 values. And why is this the case? You might pause the video if you're interested in thinking it through, but I'm going to reveal it now. It's because the skill gaps are not optimized, and therefore there might be 2 solutions with the same social satisfaction, which is the only thing that gets optimized, but they have different skill gaps. And that happens, for example, if there's a person which has no social preferences, everyone is rated 0 for him or her, and therefore he or she can be assigned to more or less any group, but this influences the skill gaps, but not the objective. And therefore the different structure of search trees of the 2 models might lead to a different optimal solution being found within the Gurobi search strategy of the branch and bound tree. What we also see is that the social satisfaction shrinks with S. And why is this the case? Our hypothesis is that you have less friends as a ratio if you're in a larger group, and therefore you're more likely to come into a group with people you don't like, in the sense that you did not give him or her any preference points and let them at 0 to just not dilute your vote. And therefore there are many people which don't know each other, which pushes the social satisfaction a little bit. And same holds for the skill gaps. The problem is in these larger instances where S is really large, like 50, there are so many groups, there's most certainly some outlier to the top or to the bottom, and therefore I think that's maybe the reason why the skill gaps get worse with an increasing number of students, even though one would have more options to distribute the skills evenly, maybe. What we also see is the diversity values, if they are not optimized, they remain more or less constant. So yeah, if there's no benefit of it, then the algorithm will produce more or less the same diversity as one would get if one employs a random assignment to the groups. And we see similar trends here for the single model, and a strong increase in running time for T, and an even stronger increase with respect to T. But keep in mind that those are milliseconds, so this is still under 9 seconds here. Social satisfaction, the same monotonicity, degrading for increasing number of people, same for the skill gaps. Diversity always between 0.33 and 0.34. What is interesting to me is the topic satisfaction, because it shows us that that many people and few topics produce more topic satisfaction than having few people but many topics. And that's because we did when we designed the distribution of our user data, which is randomly generated. If you want to know more, you can watch the appendix video. These social preferences, they correlate with each other. So groups of mates like each other. That's how we modeled it. But they must not have correlating social topic interests. And that's why just the chance of hitting the same topic with your mates, if there are few topics, is higher if there are less to choose from. So that's why more choice leads to more discrepancy within the friends, and therefore you see that the topic satisfaction is really dependent on this ratio between S and T. And now to the last two rows. Here it gets really hard to solve, because here we are at 1 second, 1.6 seconds, 2.3 seconds, and suddenly here we are at 900 seconds, about 15 minutes, and here it goes into the hours, 3-4 hours. That's still okay, but one can see that's really a strong increase. And here we have this outlier, which actually has a shorter running time than its smaller counterpart. But this comes from the fact that we have very few instances that we solved here. But the monotonicity which we investigated before is still valid. And the other values aren't too representative, because we just computed this blended approach and this hierarchical approach with different tolerances and weights, and just played around with it to get a representative running time. But then you have one model which preferences the social and topic preferences, and the other one which favors all the skill preferences. And then you have this competing interests, and we took the average, and therefore this cancels out, and you have a lackluster performance in these. But if you look at each instance itself and know what you wanted, then you can really choose your parameters such that you get what you want. But yeah, there are so many possibilities how to choose the parameters that we decided to let them run with parameters you wanted to employ, like tolerance 10%, 20% in degradation, or weights 1 to 1, 1 to 2, etc. And did not run 100 simulations for one specific ordering or something. But what is interesting about this line is that suddenly, if you really benefit from diversity, then the model actually gives you higher diversity. Not much, but it's also difficult. As I told you, you have this this problem that once you have 4 or 5 people in this raster of 0 to 1 is interval, then you cannot maximize some difference. So it's really hard to get over 0.4, I think, and it's really hard to get lower than 0.3. So this is actually significant towards in comparison to the other ones, I think. And also the skill gaps are massively bigger than the other one. But I didn't use these conditional coloring because those colorings would just blow everything out of the water here. And also the frontier, which is just, as you saw, this iterated process of calculating the multi for different weights and tolerances. We see here, this one is actually still calculating, but this is 7 hours or 8 hours. So this is really pushing the limits of our own desire to be really strongly under 1 day. So here you see some frontiers. The left frontier is for 20 students, 10 topics, and seed 0, and you can see this nice shape where you can see that none of these points is dominated, in the sense that there's no point in the upper right from it. So this is really, I think, a good approximation of the sufficient frontier, and each of this point references to one assignment of groups and on topics to persons. Here you have the S equal to 31, which took 7 hours or something, and here we actually increased the duality gap, which is allowed to be considered optimal. Here, the duality gap was 0.001. No, 0.01, sorry. And here we choose 0.1. And why is that? Because we noticed that this in this pyramid approach, on the way back, you have very infeasible problems, in the sense that the constraints on the objective, which now are not allowed to be degraded by any amount, they make the other problems very infeasible. And so we told the algorithm, if you're running maybe a specific time, then stop focusing on reducing the duality bound, because that's all what happened in the end. The primal bound did not improve by any means for really dozens of iterations, but focus only on the primal bound and stop trying to reduce the duality gap. And therefore, we were satisfied with 0.1 because it still produced a fairly good approximation. There were some points which are slightly dominated, like this one, but it was just a waste of time in the end, because it's always just the duality bound which decreased slightly. So we put this turbo into it, which increased the primal solution by a bit, and then a few minutes later it just stopped it, and it still produced fairly good results and reduced the running time to those 7-8 hours. So those are our references. The first two and the last two are specifically for literature about what is the optimal group size and what makes a group successful in terms of differences in skills and differences in especially cognitive abilities and experiences. So they are more aimed at the human sciences. And the third one is all about finding Pareto optimal solutions to multi-criteria optimization problems. This is a state-of-the-art analysis, which was an inspiration. And here we have the references to our images, which are just the logos we used in the beginning. And if you're interested in some more details about this topic and specifically about these questions, then I highly recommend to you looking at our additional material. Namely, we will also upload a video about these questions, some appendix video if you're interested and want to know more. You're very welcome in watching it, and also in leaving a comment or a suggestion under this video. We highly appreciate it. So thank you for your attention, and have a good one.